Yes, and thank you very much for say again.
Oh, no, it was an automatic message that recording is starting.
Okay. So then, yes, so thank you very much for the inviting, and it's a kind of also to me it's a special experience to teach a course for so many people which I don't know completely. So yes, so about the questions, the best thing would be so if you ask questions in chat, unless something really you will see that something really bad happening in my slides or I'm speaking complete garbage, then just interrupt me. But otherwise, try to ask questions in chat, and also I will be making stops and will be asking if everything is clear and if there are any questions. So everything is clear so far, right? Okay, so I will speak about. So the plan for this week is to speak about representative families and the applications of these families for algorithms. And the main message of my lectures will be, if you just forget everything which I will be speaking for 4 hours, I hope still the only message which I want you to keep is, look, people were doing combinatorics and graph theory already for 60, 70 years already, right? And somehow it's surprisingly that the combinatorics which was developed in, or extremal combinatorics which was developed in 1960s, still people use it for algorithmic purposes. And definitely in the times when these theorems from extremal combinatorics were developed, people had no idea that these theorems will be applied in that way. Right? So there are a lot of useful things which happened in the past, and maybe the message will be just we shouldn't forget them and we can use them creatively. So I will start speaking about Bolobash lemma, the results in extremal combinatorics. And then I will just to warm up, and this probably will be the job of the day. I will speak about some combinatorial applications of Bolobash theorem, like critical graphs or minimal separators. And then I move to more algorithmic parts. I will speak about representative sets. I will speak about Lowa's theorem. This is exactly the same Lowa's. So if you listen to the talk of Maria, so there was a Lowa's theorem about perfect graphs. There is exactly the same Laszlo Lowas who proved also the theorem about representative sets. So I will be speaking about representative sets. I will explain how to find them, and I will give you I will try several attempts how to compute representative sets efficiently, more efficiently, and I will also speak what I mean by efficient computations of representative sets. And then I immediately give you an example of algorithms, how to use representative sets to compute the longest cycle in a graph. And then I will move further. I will start speaking about matroids, and matroids will be a very useful tools to prove different things about representative sets. So I will give you one more algorithm which computes representative sets, and then I will speak about other applications in kernelization of representative sets. So again, this is only the plan, and I hope I will manage to do it in 4 lectures. If not, maybe I will have to reduce the plan, or if I speed up, maybe I will add more things. So this is just as it says, it's a plan. So any questions so far? Perfect. So let's move with an example. So just to understand what Bolobash lemma says, or what it is about, suppose you run a NASA center or the analog of NASA center in Russia. So you want to send a group of cosmonauts on the mission, right? So basically what you want to do, you have a set of 20 cosmonauts, and you need to send only 6 of them. Right? And you have to make a team. And when you make a team of 6 people, it requires sometimes money and efforts, right? Because you have to train them together. So it's not like you just can take any arbitrary 6 people and say, you are the team. No, you take 6 people, you train them. So it costs you to create one team. Okay, and there are a lot of different ways of creating your team, right? So you can create various teams. However, there is a catch there. You know, by statistics that before the flight, for sure, 3 out of 20 cosmonauts will be ill, right? And you cannot send a sick person to the space, right? So basically, you want to form some number of teams, right? So for example, in this example, so if these 3 guys are sick, then this team will not be, you'll not be able to send this team, you'll not be able to send this team, or you'll not be able to send this team, right? And if these 3 guys are sick, then actually you'll not be able, so all the teams you made, you will not be able to send any of them on the mission. Right, and those of you who had some course on set theory or on algorithms, you see that basically this is a heating set problem, right? Okay, but then so what's the difference with the heating set problem? So the question is, what will be the minimum number of teams you want to form to guarantee that for any worst case scenario, when any of the 3 people will be ill, at least one of the teams will survive, right? And well, the trivial bound here is definitely if you take 20, choose 3 teams, right? So what you do, so for every 3 potential sick cosmonauts, you select 6 which do not intersect the set. Right, so it means that all possible situations when 3 people can be sick is 20, choose 3. So and then and for each of the situations you select the complement for this team. So definitely if you form 20, choose 3 teams, then definitely at least one team will survive. But the question is, can you do better? So because again, so making a team costs efforts. So then could we find a better solution here? And actually, this is exactly what Bolobash lemma says. Yes, so Bolobash lemma, it's lemma from 1965, proved by Bela Bolobash. And at that time, Bela Bolobash was a master student. So that was yes, the one, it's, I think it was his second research paper. And if you read this paper is not about the Bolobash lemma at all. So Bolobash lemma is just a tool, he proved it there. And yeah, life sometimes is like that. So I think most of the people in combinatorics, they hardly will tell you what this paper tried to prove. This is a paper in extremal combinatorics, but everybody knows what this tool, Bolobash lemma, what was the main tool which was used to prove the result of this paper. That was what they are. Okay, so let me just state this lemma for give you a formal statement of the lemma, and then we'll talk a little bit about different formulations and how to prove the lemma. So the Bolobash lemma. Suppose I have 2 families of sets, and this is also why this lemma sometimes called it 2-family theorem also. So I have M sets A, so A1, A2, AM, and each set is of size A. And I have also M sets B. They are all the sets are over the same domain of size B. Right, view this again. So A, the sets A are the teams of cosmonauts I need to send to the mission, and the sets B are the sets of cosmonauts which can be sick. And then the sets satisfy the following condition. So for every index I, the sets AI and BI are disjoint. And for I not equal to j, these sets intersect. And then the question is, how many of such sets could be? And the Bolobash lemma says that this number m, the number of sets, is always at most as a plus b, choose b. Okay, so you can say, what is so exciting about this lemma, right? It's some lemma in extremal combinatorics, and so why I should be excited? So first of all, what is a strange thing happening here? Look, so I'm speaking about set, the number of sets of a domain of size n, right? So I have n elements, and I'm looking for all subsets there. So what is surprising thing here, that this number m, it doesn't depend from n at all. It only depends on the size of A, and it only depends on the size of B. This is already a little well, there's nothing strange because this is a mathematical lemma, so, and I will prove it. But this is somehow which is actually allowed to apply a lot of algorithmic or build a lot of algorithmic results based on this lemma. I will prove your slightly more general variant of Bolobash lemma. So for the algorithm, we use the variant of the lemma where all sets have the same size. But the original proof of Bolobash, or the original lemma of Bolobash, is a little bit more general. So the original statement of the lemma is the following. So I have m sets A, A1, A2, Am, and the sizes of the sets are A1, A2, Am. And I also have the sets B, which of sizes B1, B2, and Bm. And again, the condition is again exactly the same. So this the intersection of the sets with the same index I is empty, and the sets with different indices, they should intersect. Then the sum of this sum, I take A plus AI plus BI, choose BI, and I take it to the power -1. I take the summation of all these guys. Then the sum will be at most 1. So why it's first why this is a more general variant of this, right? Well, this is easy to see, right? Because what's happening? I just if in this formula I will or what's happening here if all cardinalities of sets AI's are equal to A, and all cardinalities of BI's are equal to B. So what happened with this formula? Well, then I take the sum from I to M, and here all the summands are the same, right? So I take the summation from 1 to M, which means that the sum is equal to M times multiply A plus B, choose B, power -1, right? And if I'm using this formula, then this value is at most 1, right? So I just what I'm doing, I am multiplying this part and this part by A plus B, choose B, and I obtain this inequality. So this is just a slightly more general form of the Bolobash lemma. And again, after several, after many years, there are different variants of Bolobash lemma. There's different conditions, but for the algorithms, for so far, for 2 lectures, I will be using only this form. Okay, so the proof, or maybe it's the right time to stop and ask if there are any questions about Bolobash lemma or a statement of the lemma.
Could you explain how it applies to the Cosmonaut problem?
I will come back to this. That's a good question. Yes, you're right. Yes, I will come back to this. But let me just first prove the yes. But Daniel, that's yeah, that's a lot. Makes a lot of sense. Yeah, I will tell you in a few minutes. Yeah. Okay, so the proof is called, it's based on the idea of counting permutations. And this is definitely the proof which I will call a cute proof. So and the definition of the cute proof, it should be simple, but it should be simple only after you see the proof. Right? And because well, if somebody will ask me to prove Bolobash lemma, I will probably start to make an induction, and by making an induction, you can also prove it. So that's no question in that. But the proof, you will have to make some kind of quite unpleasant inductive assumptions. So it's also will be a proof, but it could be a not so beautiful proof. But this proof is cute. Okay, so the main idea is, so suppose I have two sets which do not intersect, and I take a permutation of the elements, right? Then I say that permutation x1, xn separates the sets A and B if for every element xk from A, so here is an arrow, here should be xl, and xl in B, it implies that xk is smaller than xl. So in other words, it means that in these permutations, all elements of A are to the left of elements of B. Right? Okay, then my claim is that every permutation separates at most one disjoint pair A and B, and which satisfies okay, once again, so the claim is that if I take the sets from the statement of Bolobash lemma, A's and B's, right, then this permutation, it separates at most one pair. Why? Okay, suppose not, right? Suppose there are two sets AI, BI and AJ, BJ, which are separated by the same permutation. Right? So in this picture, one pair is separated by permutation, all AIs are to the left from BIs, and all AJs are to the left from BJs. Okay? Well, what we know by the condition of the lemma, so for every pair of different indices, the intersection of AI and BJ is not empty. So here I know that AI and BJ is non-empty, and also AJ cross BI is also non-empty. Right? But how this could happen, right? So, well, if I have set BI and I have the set BJ, well, some of them should be a little bit, so the smallest element of BJ either should be smaller than the smallest element of BI, or the smallest element of BI should be smaller than the element of BJ, right? So let me just BJ, the smallest element of BJ should be smaller than any element of BI, right? But BJ, it should cross as AI. But on the other hand, AJ and BJ are disjoint. So then AJ, it cannot cross BI. Right? This means that our assumption that there exist two pairs which are separated by the permutation was wrong. We are almost done. What remains, so that was the most crucial observation. Now what remains is just to do the counting. Okay, so how many, now I want to count how many permutations separate a pair A and B, which is disjoint, right? Okay, so let A be the size of A, B be the size of B. Now, how many permutations which separates A and B? I do the following counting. First of all, so how many choices I have to select elements of A and B? Right? This is N choose A plus B. This is the amount of choices I have to select for the union of for the elements of A and B. Now, as far as I selected these elements of A and B, I have A factorial permutations of for elements of A, and I have B factorial permutations for the elements of B. Right? And for the remaining elements, which are not in A and B, I have M minus A minus B permutations. Yes, somebody is helping me to draw the lines on the on the screen. This is a okay. Hope it will not happen too often. Okay, so then and then I'm just I'm writing just definition. What are the binomial coefficients, right? In the formula in terms of factorials. So n choose A plus B is n factorial divided by A plus B factorial and divided by this factorial, right? So when this part reduces, so then at the end I will so when I do this transformation, I obtain that the amount of all permutations here is equal to n factorial times A plus B, choose A minus 1, right? Okay, almost there. Now, so this is the total amount of permutations I count, right? But now I am using now the claim that every permutation, it separates at most 2 pairs, which means that in this sum, there's no permutation which is counted twice. But the total amount of permutation is n factorial. This means that this sum doesn't exceed n factorial. So if I divide by n factorial, this is exactly the lemma I want to prove. Any questions so far?
Would you upload your PPT slides anywhere?
Will I say again?
Would you be able to upload your presentation slides somewhere so we can like double check it again?
Sure. Yes. Sure. But it's. I think it's better to do it centralized because probably the same will be with the Madhusudan lectures. So maybe it's just Dmitry will take care of that. But definitely, and if not, yes, I will put them somewhere.
Thank you.
Yeah. I think the easiest thing I just will send them to Dmitry, and then he will just upload it to the school webpage. That's probably will be the best, the easiest solution. Yep.
Yeah, sure. I will upload it there.
Okay. Yes. So that's the proof of the Bolobash lemma, and actually now even the simple one. So because probably behind this counting arguments or counting permutation arguments, you will see what he is doing, right? So why he just doesn't use the probabilistic argument, right? And of course, what I was explaining in the previous proof is just yeah. So yes, you can definitely do the same randomized proof of the same type of lemma. So this is just the proof number 2, but actually it's not the proof number 2. It's just the same proof in a slightly different language. So what I'm saying, I want to prove the same lemma. Now I want to use just probability argument. So I just take pi as a random permutation of integers from 1 to n, right, of the elements. So what I proved in the previous slide, right? I proved that the number of permutations separating A and B is n factorial times A plus B, choose B, power minus 1. Right? This is what I proved you just a few seconds ago. This means that the probability that this permutation, that a random permutation pi separates A and B, right? So I have n factorial permutations, and from them I select randomly one, right? And I know that the number of separating permutations is n factorial a plus b choose b minus 1. So this means that the probability that I select the one which separates a and b is exactly this number. Now, what I also prove you, right, that no permutation can separate two sets. This means that the events that pi separates ai and and bi, and pi separates aj and bj, here should be I, not j. These events are disjoint, which means that if I take the sum of all these events, right, the probability that this happens is at most 1. So it depends what of matter of your test. You like the first proof better, you like the second proof. And actually, as for every good result, there are other proofs. And I will speak. I will mention if you're interested and you want to read more, I will give also the reference for that later. Okay, now coming back to the question of the cosmonauts, right? So what is the application of the Bolobash lemma to the cosmonaut selection? Okay, so once again, I have a Bolobash lemma, right? And the observation is the following. Suppose that I selected the minimal family of sets of size A, right? And the minimal, I mean inclusion minimal sets. So if, such that for any set B of size B, there is the set AI disjoint from B. Right? View it again. So as with cosmonauts, right? You want to select the teams. You don't know which people will come sick. You know only that there will be the group of 3 people will become sick in the future. You don't know who of them, right? So, but you want to be sure that at least one guys or at least one team from your family will be disjoint with the sick people, right? Then the claim is that for every I, there is a set BI of size B disjoint with AI and intersecting all other sets AJ. So it means that for every set AI, you can select its own representative. And why it's so? Well, if it's not like that, right? If there is a one AI and there is a set BI which is doesn't intersect it, and there is another one, then you just can throw away one of these AIs, and this will contradict the minimality of your set, right? So you can always. So what I want to say that if you have a minimal family of sets of size A, such that for any set of B of size B, there is at least one guy who is disjoint with the set B, then you can always assume that these sets, they satisfy this condition. So that you have the sets A1 and AM, and you can select the sets B from B1 to BM of size B, such that for every I, the sets AI and BI are disjoint, and the intersections of AI and BJ is non-empty. Then, by Bolobash lemma, we know that this set, the size of the set, the number M, the number of sets in this family, doesn't exceed A plus B, choose B. So coming back to the cosmonaut example, right? So what we are looking for? We're looking for sets of size 6. These are the sizes of the sets A. And the sizes of the sets B are 3. So we know that to secure this condition that there is always will be a team not infected, we just should select 6 plus 3, choose 3. It's 9, choose 3. And I was lazy to do this computation, to compute what is a 9, choose 3. But for sure, it's much, much smaller than 20, choose 3. Yeah. Okay. Questions? Okay, so just an easier, just to show that the beauty and the power of the Bolobash lemma, let me just prove some result which is called LIM inequality due to the names of Lubel, Meshalkin, and Yamamoto, who proved this inequality independently. And at that time, you see, so what means independently, it's 1966, 1963, and 1954, right? It's like the same when you read about Cook-Levin theorem, right? And you see, oh, at what time it was proved. This discrepancy in times at that time could be quite big. So yes, times are changing now. If you put a paper on archive, right, this is if somebody prove it 2 days later, doesn't make any doesn't make any difference anymore, or it makes a big difference today. Anyhow, so yes, so this is the people who prove this inequality independently, and sometimes it's also even called BLYM because this inequality follows trivially from Bolobash lemma. Okay, so definition: what is an anti-chain? So a family of sets F is an anti-chain if no set of it contains another. So in other words, if I take any two sets from this family which are not equal, then one is not contained in the other. An example, so for example, if I take a universe of n elements, and then I consider the family of F as the sets of, or as all sets of size exactly k. Right? So then no set of size, no two different sets of size k are contained in one another, right? And so this is a definitely anti-chain, and the size of this anti-chain is n choose k, right? And you can ask if there is anything better. And actually there's an inequality says that if I have a anti-chain on set x of n elements, then actually the sum, then this sum, I take the sum over all sets in the family, and then the sum is at most 1. How come? Well, let me just to write this as the sets as we do for Bolobash lemma. So I just take the set F to be the set of families A1 and AM, and then I put the set BI to be equal as all remaining elements which are not in the set AI, X minus AI. Then what is this sum? Right? Well, n. So because every BI is the complement of the set AI, right? Then the n is equal to the size of AI plus the size of BI, right? And here I can have take the sum over AIs, and this is equal to the same AI plus BI choose AI is equal to the AI plus BI choose BI, right? This is a again, simple property of binomial coefficients. So I take this sum, and by Bolobash lemma, the sum is at most 1. So here we go, right? So this is yes. So the second application is also quite old. It goes for critical graphs. And what is a critical graph? So critical graphs are the graphs. Okay, so definition. So first I need to define a critical graph. I need to define what is a vertex cover of a graph. So a set of vertices S is a vertex cover in a graph G if every H has at least one point in G. So in this example, I have a graph on 5 vertices. And these 3 red vertices, they form an H cover, or sorry, they form a vertex cover of this graph, because every H is adjacent to at least one of these vertices. And actually, if so, the vertex cover of this graph is exactly 3, right? Because if I remove any of these vertices from the vertex from the set S, then at least one H will be uncovered. Okay. And then the definition, the graph is HK critical if its vertex cover is, yes, and the vertex, if its vertex cover is of size K, but for every H of the E of this graph, if I remove the H from the graph, then the vertex cover drops by 1. Right? I have a graph of vertex cover of size K, and then if I remove any H, the vertex cover decreases by 1. So example, so the complete graph on K plus 1 vertices is K critical. How come? So first of all, why the vertex cover of a complete graph is K? Well, on this example, so the proof is by example, right? I take a graph on 4 vertices and I construct, and I take any 3 vertices, and then this will be the vertex cover of the whole graph. And also the same argument, they work for any number of vertices in the complete graph, right? So K plus 1 vertex complete graph has a vertex cover of size K. And now, so it requires arguments that if I remove any H from this graph, right? So if I remove any H from a complete graph on K plus 1 vertices, then the vertex cover will be K minus 1. Right? So it's not a difficult argument, but as an exercise, just I don't want to explain it. So please try to prove it as an exercise. It's, okay. Yes, and this is the classical theorem, another classical theorem in extremal graph theory from 1964, the theorem of of Erdős, Heinel, and Moon. It says how many ages could be in a K critical graph. And the theorem say that every H K critical graph has at most K plus 1, choose 2 ages. So, and this type of arguments, this is again, so those of you who know about kernelization and parameterized complexity, at this moment you will start saying, oh, probably I see something familiar or useful. But if not, I will try to explain it in a few lectures from now. But so far, view it as this strange arguments, right? So you have a graph with a vertex cover K, and actually you take an H and you want to remove this H, and you want to argue if the vertex cover of your graph will decrease or not. The funny part of this type of arguments is that look, somehow, or the interesting part from the algorithmic perspective is that vertex cover is an NP-complete problem, right? So when I give you a graph and I tell you, is this graph is a K critical, can you remove the an H such that is it true that if I remove any H, then this vertex cover will drop? You don't know how to solve this problem efficiently. Right? But there are combinatorial arguments saying how many edges in this graph should be. Okay, so how to prove this theorem? So every HK critical graph has at most K plus 1, choose 2 edges. Okay, let's take a critical graph, K critical graph G, and let just its edges be E1, E2, and EM. These M edges. Now, by the definition of a K critical graph, right? So for every H, E, I, and you can view, think about an H as a set of size 2, right? So the endpoints as the vertices of the H is the H, right? It's an H of size 2. So there is a set Si of vertices of size K minus 1 that does not intersect EI and intersect all other edges, right? Once again, because the graph is K critical, it means that for there is a vertex cover of size k, and if I remove any h, like HAI, there should be a vertex cover of size k minus 1, right? So why is this happening, right? If for every set S of size k minus 1 that doesn't intersect HEI, but and also doesn't intersect some other h of this graph, then I just can remove the HEI from the graph, and the remaining graph still will have no vertex cover of size k minus 1. But then it's not k critical, right? Okay, so then let me just write it in the, again, this statement. So in the form of the Bolobash lemma. So I have a set from E1 to EM. These are the sets of size 2. I have the set of, so the sets S of size k minus 1, right? And I know that this is what I wrote here, that for every HAI, every set EI is disjoint with the set SI, and every set EI intersect set SG for every I not equal to J. Right? But then how many of such sets M could be? Well, so again, I'm just using Bolobash lemma. So here is a k minus 1 plus 2, choose 2, which is k plus 1, choose 2. Any questions? Well, so the last application of the day is comes from a different area. So it's about counting sets. And the usual question is how many specific objects are in a graph. So just, for example, how many independent or stable sets are in a graph, right? So the set is independent if there's no, a vertex set in a graph is independent if there's no edges between any pair of the vertices of the set. Well, so then the question for, so how many different independent sets in a graph can have, or what is the largest number of different independent sets that could be in a graph? Well, this type of questions at first glance, they are not so interesting, right? Because what's happening here? I just take this graph, it's a star with n vertices, right? And basically any subset of the leaves of the star is an independent set. So this is like 2 to the n minus 1, and actually, even if you ask what's happening if the set is connected, then it's again, so you can say, okay, there's again at most, there is always could be 2 to the n minus 1 sets. So, and basically this is not much different from just what is the number of different vertex subsets in the graph. Yes, it's 2 to the n, right? So nothing interesting. However, if we change the question, how many maximal independent sets are there in the graph? So I have a graph with n vertices, and I ask how many maximal independent sets could be in the graph. And maximal independent set means that if I have an independent set and I add any, if I have a set and which is independent and I add any vertex to the set, then this will not be independent set anymore, right? So it's inclusion maximum independent set. Okay, well, definitely there is an example of graphs which have 3 power n over 3 maximal independent set. This is example. I just take, so if my graph has n vertices, I take n over 3 disjoint triangles, right? And then every maximal independent set contains exactly 1 vertex of each of the triangles. Right, so then I have 3n power over 3 possible maximal independent sets. The funny thing that, and this is again, it's another classical result of Moser from 1965, that actually there's no graph which can have more than 3 power n over 3 independent maximal independent sets. And the proof of this is branching. So basically, and why number 3 comes here? Well, because just 3, 1 over 3, it maximizes the value of the function x power 1 over x over natural numbers. And why? So I just will briefly give these arguments. It's what called in algorithms branching, recursion, pruning search tree arguments. That's all about the same. So so what I want to prove? I want to prove that the number of maximal independent sets in a graph on n vertices. I want to compute this number. Okay, so if I take vertex v in a graph and I take its closed neighborhood is the vertex itself and all vertices adjacent to this vertex. Then at least one vertex from the closed neighborhood should be in the maximal independent set, right? Okay, so then if the vertex v was of a minimum degree, yes, I know that maximal independent set should contain a vertex from its closed neighborhood. And then I can continue recursively, right? So I can say that the number of maximum independent set in a graph is at most the sum of maximal independent sets of the new graph. So I go through all closed neighborhood of the vertex v, and I just remove from the graph the closed neighborhood. And then, yes, if the vertex degree, the degree of vertex v was d, then the size of the closed neighborhood is d plus 1. And here, every time I remove d plus 1 vertices. So this is the formula for my recursion. And then, yes, when I rewrite it, yes, there's also should be argument. You probably have to do some differentiation to show that the maximum of this function is reached when for the value when d is equal to 3. Right, and then it just gives you this bound. And actually, there's a lot of this is in the area of exact exponential algorithms, where people try to design algorithms which are still exponential, but which are better than the brute force. And this is this branching is a standard technique for this type of algorithms. And people were doing a lot of computing how many maximal bipartite graphs. And here you see there's a bound, the lower bound and the upper bound, which are not so for maximal bipartite graphs, for example, it's not so good as for independent set, which is like for minimal dominating sets, for subsets, feedback vertex set, whatever it is, right? So there were a lot of branching algorithms. So what I want to tell you, for the last 10 minutes, the algorithm which enumerates another interesting objects in a graph, but it uses not a branching, but it uses a Bolobash lemma. Okay, so what is an A and B separator in the graph? So I have vertices A and B, and then the A-B separator in the graph is the set of vertices such that if I remove these vertices, A and B will show up in different components. Right? So in this example, this is a separator, this is a separator, and this is a separator. And then a separator is AB minimal separator, or minimal AB separator, if its inclusion minimal. So this separator is not inclusion minimal, right? Because it contains this separator. And it also actually contains this separator. But this and this are minimal separators. So the question is, how many minimal separators could be in an n-vertex graph G? So the trivial bound, of course, is at most 2 to the n, right? Because separator is a vertex subset. So if I try all possible vertex subsets in an n-vertex graph, I will have at most 2 to the n. And the theorem I want to okay, I have two options. I have option number 1. I start speaking fast, and then I will manage to prove the theorem in the remaining 10 minutes. And then I will be unhappy, and probably most of you also will be unhappy. Or I just can stop at this moment and start proving this theorem tomorrow. and then I will go through it. At least it will be hopefully understandable. And yes, I think I will not be able to prove this theorem in 10 minutes. So I just will prove it tomorrow. So far it's just a spoiler. What's happening here, right? Okay. And so far, I just want them to conclude the lecture of today. So after we spoke for 50 minutes about, or 55 minutes about Bolobash lemma, you still can wonder, okay, so this is, yes, agree, maybe this is some fundamental result from combinatorics from 1960s, but why we should care about this today? Well, one answer could be, well, it's a beautiful result, and it's also, it will be nice to know, right? But also it's actually, I'm more pragmatic, right? And my area of expertise are algorithms, and definitely this is something which I want to use for the algorithms. But so far, I will not tell you how I will use it for algorithms, and we will start from algorithms tomorrow, right? But so far, just please be aware that we care about this not just because of the curiosity, or not only because of its mathematical beauty. Right. So for the further reading, so if you like, or if you thought that this type of results could be interesting, there's a very beautiful book of Stasis Yukna, Extremal Combinatorics. It's highly recommended, the second edition, and it's really it's a pleasure to read, and there it contains a lot of different things. And actually, somehow, to me, the most surprising thing was that Yukna himself, he is not a person who works in extremal combinatorics. He just uses this, but it's but the book is very nice, and yes, it's highly recommended. And also, like if for modern times, right, if you have problems with reading books, right, there's also very nice and beautiful lectures of Sang-Il Ohm on combinatorics, and it covers a lot of extremal combinatorics. So it's that was recommendations. And yes, that's I will stop here, and we'll be happy to answer the questions. Okay, thank you. Yes, yes. So the first question is Helly lemma connected to it? Yes, because Helly lemma is also the result about the combinatorics, right? About the convex sets. It's definitely if Helly lemma follows from Bolobash lemma, I don't know. This is probably not. At least I cannot say like that. Yes, very nice. Okay, Alexander Sheny. Okay, in fact, you don't need the computation. But Alexander, what do you mean by for what part you comment? I cannot hear you.
You just made some computations with binomial coefficients, but you can just say instead trivial computations. But you can say instead that you take a random linear order on the elements on n elements.
Yes.
And the question is, what are the probability that all elements of A precedes all elements of B?
Yes.
So if you restrict this random ordering to A union B, then we have a random order on elements of this A and B.
Agree. But
So we
I
have
already
just
did the job before that, right? so maybe I'm a greedy person, but I didn't want to lose already the computations I did on the previous slide for that.
No, you don't need any computation. You just say that there is only one. You get a sequence of a random ordering on A and B, gives a sequence of A, B, 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 A, B, something.
Correct.
And the sequence is random, and only one sequence is good for you. So, no, okay,
point.
you know.
Good point.
You say
I agree. I overdid it. Yeah.
Yeah.
The references would be great. I think, yes, for the Bolobash lemma, the Stasis Yukhno book. Tomorrow, please, could you give us the gist of the theorem? I think it's the. So what do you mean? Could you give us the gist of the theorem? And where the Bolobash? Okay, that's will be tomorrow. Yes, and not are there example of exponential bound where after lots of non-trivial efforts, people manage to get matchings lower and upper exponents. I'm not sure. So for independent set, this is yes the lower and upper bounds matching. But for all other examples, I know even like if you're looking for feedback product set and tournaments, still there is always some gaps. I don't know. That's a nice question about yes. The question is: are there any examples of exponential bound where after lots of non-trivial effort people manage to get matchings lower and upper exponents? Doesn't look. It looks like these questions become quite difficult. So it's okay. So Marcus Wilhelm regarding the cosmonauts and Bolobash lemma. Didn't the lemma not only say that for any sick cosmonauts we will find a team of healthy cosmonauts, but also that all other teams will be sick? Yes, if it's a minimal set of teams, yes, right? Because if you manage to construct a family of teams such that for any attack, right, or for any disease cosmonauts, there will be 2 teams, right? Then you can definitely will throw away one team, so and save on forming the team. So again, so when you're looking for the minimal set, it will automatically satisfy the condition that all other teams will be sick except one. Can you give please go over proof of 3 one more time? Sorry, no, it's like this was just the proof I wanted to give. So probably just go to the exponential algorithm book. So that will be so that it's a branching, and basically the only it's deviate from from the main line of the lecture. I just wanted to give you the gist of what's happening with most of this enumeration algorithms, which are based on branching. And but it's we started with okay. Oh, true. Thanks. Okay, then see you tomorrow then.
Thank you for the amazing lecture also.
Yeah, bye.
Bye.